Hello everyone, welcome to the next lecture of week 9. So with this lecture I'll finish mutation testing or syntax based testing. So this was what we had as an overview picture of mutation testing for various software artifacts. So I said through the span of my lectures we would look at mutation testing along these lines. Here is an update of what we have done and where we are. So what did we discuss? Mutation testing or syntax based testing is of two kinds. One directly based on grammar, the other based on mutating programs. Grammar based testing can be applied for programs and mutation can be applied for programs. Grammar based testing cannot be applied for integration, but mutation based testing can be applied for integration. Both grammar based and mutation based can be applied for specifications. And again, both grammar based and mutation based can be applied for directly testing input spaces. What have we done? We completed all the things that are marked in green. We did grammar based testing for programming languages at an abstract level. I told you what the coverage criteria on grammars are. We also did mutation testing for programs at the unit testing level, and later on we specifically looked at mutation testing for design integration of generic kind, and we went on and looked at mutation operators for specifically testing object-oriented integration, like for a language like Java. I told you that next we will do what is called input space partitioning based mutation with XML as one case study, where I generate mutation based on grammars of input spaces, specifically for grammars of XML formats for inputs in many languages. So that will be the focus of this lecture, and as we continue to say, the ones that are striked out we will not do because it's slightly outside the focus of this course. So this lecture we are going to look at grammars for inputs. Grammars for inputs are again given in Backus-Naur form as a context-free grammar specifically, or as a regular expression. And when are they used? What are they used for? They're used for defining precise syntax of how the inputs look like. Most of the times inputs may not be just a simple integer or a boolean value or a floating point number. Inputs will have a lot of structure. Input could be an entire web page, the form that you filled into a web page, the data that you read from a database. It could have a lot of structure. Inputs with a lot of structure are described using formal languages, specifically regular expressions or grammars. For example, consider a program that operates as a part of a banking system, and let's say that program processes the sequences of deposits and debits. So the format of deposit will look like this. It will say deposit, which is like a keyword which tells you the action to do this amount into the account. Similarly, the format for debit would be debit, which is like a keyword, this amount into this account. Is that clear? Now, what are the transactions that you can do as a part of a bank account? You can either deposit an amount into an account, or you can debit an amount into an account, and you can repeat this transaction any number of times in any order. So this is the regular expression that describes the input transaction sequence. So it says the input transaction is given as a regular expression, which is the star of two entities. The first expression says deposit account amount, which says deposit this amount into the account. The second expression says debit account amount, which means debit this amount, the given amount, into the account. There is an or connecting them, which means you can do one of these actions, and after that there is a star. Star in regular expressions, as we saw, indicates that you can do 0 or more occurrences in any order of either this or this, which means you can either deposit a given amount into an account, or you can debit a given amount from an account, and any bank transaction is a sequence of inputs of arbitrary deposits and debits. Now, this could be an input. How do you read this? You say deposit into the account number 739, this amount, $12.35. Similarly, you could say debit into the account number 544, the amount $20. So regular expressions, this is simply given as a regular expressions, but sometimes, as we saw, regular expressions may not be enough, and you might need slightly more expressive structures like context-free grammars or arbitrary grammars, which can be expressed in a normal form like Backus-Naur form. So here is the same sequence of input transactions. In this slide, I had given it to you as a regular expression. Here, I am giving it to you as a grammar. How do I read it? I read it as follows. So what is a bank? Bank bank transaction. Bank transaction is a sequence of 0 or more actions denoted by action star. Then the next rule says action could be a deposit or a debit. DEP for short form for deposit, DEB short form for debit. A deposit is basically deposit, the keyword deposit, some amount into an account number. Debit is similarly the keyword debit, which depicts a fixed action of an amount into the account. Account is typically a 3-digit number. Amount is given in dollars or any currency, and it's one or more digits followed by a decimal point, followed by at least 2 digits. Digits could be anything from 0 to 9. Is that clear? So using this grammar, I could derive an expression which looks like this. So I could say either deposit a particular amount, which is this, into this account. What does it say? It says account is always a 3-digit number and amount is always in dollars in this case. It has one or more digits, which is denoted by digit to the power of plus, means one or more digits. It can't be 0 digits because you have to deposit or debit a non-zero number. And it could also have decimal digits up to 2, decimal point 2. Is that clear? So how do I derive tests from these grammars? Tests are basically input strings that are derived from the grammar. How do I derive? You follow the normal notion of derivation that we saw for grammars when we began mutation testing last week. So what does the normal notion of derivation go like? You begin with the start symbol and you designated start symbol, and you use the production rules. Keep applying production rules by picking up one non-terminal that is available at any given point in the string derived so far. Replace that non-terminal by picking an appropriate rule that replaces that non-terminal with another string. Keep doing this till you are left only with a string of terminals. In other words, no more non-terminals to replace. When you stop there, that's the string that you derive, and that belongs to the input space corresponding to the grammar that is given for that particular software artifact. Whenever grammar is not available, you might wonder, how are we going to use it? Usually it is very wise to be able to, as a tester, derive the grammar yourself from an informal description of the input given. Some description or the other of the input will always be given because the software artifact and its input have to be described. Otherwise, software development doesn't progress. But to be able to automatically derive tests, you need grammar notations, which are syntactically formal notations for describing inputs. If it is not there, then as a tester, it's completely worth spending some time deriving the grammar from the informal description given. In the past, empirical studies have shown that just this exercise of deriving grammar from an informal description of the input sometimes unearths non-trivial bugs or vulnerabilities in the inputs to the software. So it's a valuable exercise in its independent right and is also useful for mutating and producing inputs to a grammar. We will see XML as a specific example because it's a very popular input format that is used across several different applications. So what is XML? This module is not intended as an exhaustive introduction to XML. Please feel free to read up details about XML from other resources. I assume that you know some basics of it, and I will use it mainly as a language to describe inputs and as a case study to show you how test cases are generated from the input. So XML expands out to extensible markup language. It's a language for describing inputs that have a lot of structure in them. It's popular across many applications. Typically, it's popular across web applications and web services. Of course, I basically work with a lot of embedded software design and development, and if you see, almost all the languages that I work with, which is Simulink, AADL, which are a proprietary embedded design and architecture language, they all have XML to describe their input language format. So XML, like all other structured formats, has a built-in syntax or a grammar to describe. The built-in syntax or grammar that is available in XML is what is called a collection of schemas. We will not introduce schemas thoroughly, but you can look up schemas from any standard book or reference on XML. In addition, XML inputs use a notation called tags. What are tags? You can think of tags as some kind of textual description of data, and the textual description of data is enclosed within angular brackets. Angular brackets means this is the opening of the tag, this is the closing of a tag. Each tag comes with this angular bracket, and then for each open tag there is a corresponding closed tag. Inside each tag there is some kind of a structured text that is described. Typically we note that all XML messages must be well formed. What do we mean by that? They typically have a single document element with other elements properly nested within it. There is a structure that is described in a nested fashion, and every tag, as I told you, that has an opening tag must also have a corresponding closing tag. So in this sense, if you know HTML, which is an old language, it's a lot like HTML. It's another markup language, but of course it has a lot more sophisticated, richer language to describe structured data formats. So here is a simple example of how an XML message for books will look like. So what does it say? If you ignore the first 4 lines, we'll come back to that. It says, you concentrate on this. So it says book opening tag is here. The corresponding closing tag is here. So the opening tag is given by this angular brackets book. The closing tag is given by the angular brackets book with an additional / here. Now, what are the further structures that are available inside the tag book? Inside the tag book, there could be several other tags. ISBN number is one tag. Title of the book is another tag. Author is another tag. Publisher is another tag. The price of the book is another tag. And the year in which the book was published is another tag. Of course, this is not exhaustive. You could have additional details describing the book. Like, for example, you could say whether it is which edition, first edition, second edition, whether it is a paperback, and so on. And if you notice, each of these subtags have an opening tag and a closing tag. And the syntax is fairly clear, right? So opening tag looks like this within angular brackets. After the text that comes inside the opening tag, there is a corresponding closing tag, which is the same as opening tag, has angular brackets, in addition has a /. So it says each book tag has ISBN number, title, author, publisher, price, and year. So this describes one book, the book with this number, title, Art of Software Testing. Author Glenn Mayers, publishers Wiley, price is $50, let's say. Year of publication is 1979. Now there could be one more book tag, which again gives the same details for another book. That book's ISBN number is this. The title of the book is called Software Testing Techniques. Author is Boris Beiser. Publisher is Van Nostrand Reinhold. Price is so much. Year is 1990, and so on. So, and what is the top part? Top part is some kind of a header information. It tells you which is the version and the encoding of XML that you're using. And this is a comment which tells you that this is a sample XML file meant to describe books. And this is the place where I kept the schema from. In this schema, books.xsd, which I've kept here, I can describe the following, which I have not given you the schema. Please note that we have not described the schema, but I'll tell you in English what the schema will describe in structured language of XML. So it says, the schema will say the following. It says this books, which begins here, XML message can contain any number of book tags, which are these. There's one book tag here, 2 book tags that I have shown. Each book tag contains 6 pieces of information: title, author, and publisher, they are strings. Price is a decimal numeric, has 2 digits after the decimal point, lowest value is 0. There will be a schema to describe this within XML. I have not given you the schema, please remember that, I have just described it in English. ISBN is a number that has up to 10 numeric characters. Year is an year with 4 digits. And once I have the schema looks exactly like my grammar. It has terminals, it has non-terminals, it has rules that tell you how strings of non-terminals and terminals can be derived. And so I can use the same criteria that I told you for grammars when we did that module to be able to derive XML messages for test inputs. In this case, the test input will be a specific book or a specific set of books, and I use the grammar to be able to derive those books. The grammar is obtained directly from the schema description of the XML message. Now moving on, when I consider mutation for input-based grammars like XML or any other grammars, while testing a program, what is the tester? In addition to normal inputs, the tester, it is also useful if the tester provides malformed or invalid inputs. Why are invalid inputs necessary? Invalid inputs are necessary because it helps to check if the program does fault handling correctly. Invalid inputs also imply a lot about the core functionality of the program on correct inputs. If the program works correctly on invalid inputs also, then there's definitely something wrong with the functionality of a program. Typically in areas like security testing for embedded systems, they insist that you do test with invalid inputs at every level, specifically at system level, and they have known to reveal a lot of vulnerabilities in the system. Just as we saw that standard mutation operators for input grammars can be used to generate valid inputs, mutation for input grammars can also be used to generate invalid inputs. Once you generate an invalid input, you give it to a software artifact like a program and see how the program behaves on that invalid input. Now we'll see what are the common ways to create invalid inputs by mutating grammars. Common ways to create valid inputs by mutating grammars we already saw when we introduced grammars. Now I'll tell you how to create invalid inputs by mutating grammars. Please note that when we mutate grammars, the mutants that we create are the test cases themselves. This was not the case when we mutated programs. When we mutated programs, we started with a program, if you remember, we called that program a ground string. We mutated that program. The resulting program that we got was another program that had to be tested. We had to separately write test cases to kill the resulting mutant program. When we apply mutation for input space grammars, the mutated string is directly the test case, right? So there is no notion of killing, ground string, those things don't exist. And the test case could be valid input, the test case could be an invalid input, and that as is acts like a test case. So here are some standard operations to mutate grammar. What does grammar have? If you remember, grammar has non-terminals, terminals, production rules, and a designated non-terminal called the start symbol. So the mutation operators that we will see will basically work around these entities of a grammar. So the first mutation operator that we will see is what is called non-terminal replacement. What does it do? Every non-terminal symbol in a production rule in a grammar is replaced by other non-terminal symbols. This is a very generic mutation operator. Remember, typically large grammars for inputs, typically XML grammars, will have several different non-terminals. So this says you can pick up any non-terminal, replace it with any arbitrary non-terminal. So it is like having probably dozens or even hundreds of rules just of this kind. As always, while doing mutation, you have to pick which are the non-terminals that I want to replace to create the invalid inputs that I want to test the program for. And pick only those. Don't randomly apply non-terminal replacement for replacing every non-terminal. It doesn't make sense. For example, if you remember this grammar, I'll go back to that slide and show you the grammar for a minute. This was the grammar that we had, which basically gave a sequence of input strings that either could debit an amount or deposit an amount from a particular account. So for that grammar, we had one of these rules which says a deposit is a string called deposit with the keyword, and it deposits an amount into the account. Which are the non-terminals here? The non-terminals could be amount or account. Deposit within quotes is like a terminal string. It's meant to be fixed. It's meant to indicate a keyword called deposit. So the non-terminals are amount and account. So if I consider this mutation operator, I can replace amount with account, amount with something else, and so on. That's what the first mutation I have done. The first mutation, I have taken this production rule, replaced this non-terminal account with another occurrence of non-terminal amount. So instead of depositing an amount to an account, you just give this invalid input which deposits an amount into an amount. So we'll see how the program that handles these input transactions will manage this input. Ideally, it should have some exception handling to manage this. Another mutation that I could create would be to replace an amount with a single digit number. This would be a valid mutation. It will not produce an invalid string. Maybe it will be useful for testing what the program does on this particular valid input. So these are just examples. Again, non-terminal replacement says that when you have a production rule in a grammar, you could pick any non-terminal and replace it with any other non-terminal, both to produce valid inputs and invalid inputs. In this example, we took this. It had two non-terminals, account and amount. First mutation that I created, I replaced the non-terminal account with amount. Second mutation that I created, I replaced this non-terminal amount with the other non-terminal that I had in the grammar, which was digit. This resulted in an invalid mutant. This resulted in a valid mutant. The next rule for mutating grammars would be, instead of replacing non-terminals, you do terminal replacement, which means every terminal symbol in a production is replaced by other terminal symbols. Again, this is a very generic rule, can create several different mutants, some of them completely junk, inappropriate. It's up to us as testers to pick and choose the one that we want wisely. For example, suppose I had this rule, which was also a part of the grammar, amount equal to dollar and one or more digit followed by a decimal point followed by exactly 2 digits, which basically gave the amount that could be deposited or debited with reference to an account. That can be mutated by replacing this dollar with a dot. That will create an invalid mutant. We will see what the program does. Second kind of mutation replaces this dot with a dollar. We'll see what happens, because the ones within codes are terminals and I'm considering terminal symbol replacement. So I can't replace digit. So I replace only the terminals. The third mutation, what does it do? It replaces the dot with a 1. So all these 3 mutations, which replace one terminal symbol with some other terminal symbol, create what are called invalid mutants, which could be used to test how the program that deals with these bank transactions handles these invalid mutants. So if I apply the first mutant, I'll get a test case that looks like this. The program should figure out that this is junk input, handle it. Similarly, if I apply the second mutant, I get a test case which looks like this, which is also junk input, program should handle it. Third one is not a junk input. It says you deposit a fairly large amount into an account. If you have it, why not? The person is lucky. So the third kind of production rule says you delete the terminals and the non-terminals. Every terminal and every non-terminal in a production is deleted. Of course, if you delete the whole thing, you'll have no grammar left. So you pick and choose a subset that you would want to delete and see when the restricted grammar is applied, it will generate obviously lesser input strings. What happens to that? For example, there was this production rule that we had in the grammar for bank transactions. This can be mutated to create the following. I just delete the terminal deposit from that rule. That's the first mutant that I get. Second mutant, I delete the account from the rule. So I just get deposit amount. Third mutant, I delete the amount from the rule. So I get deposit account. All 3 of them will produce junk or invalid or malformed test cases. We have to figure out what the program does. If the program doesn't handle exceptions on these test cases, we have to build in those exception handlers. The next kind of production rule is, instead of deleting them, you duplicate terminals and non-terminals. Duplicate means what? You create another copy of one terminal or one non-terminal. Again, please remember, always in mutation testing, only one mutation at a time. So don't duplicate 2 terminal symbols, or in this case, don't delete 2 non-terminal symbols or terminal symbols. Only one operator at a time. So because I duplicate, the term for duplication in computer science theory is called stuttering. So this duplication operator is also called a stutter operator. For example, if I consider the same thing, deposit, which says deposit into an account an amount, it can be mutated by replicating the word deposit twice, by replicating the non-terminal account twice, by replicating the non-terminal amount twice. All the 3 cases, except for maybe not the last one, the first 2 cases, it will create invalid test cases, because the program cannot handle 2 keyword deposits. Second case, the program cannot handle 2 account numbers. In the third case, the program may or may not handle the amount based on whether there is a space or not. If you include the space, then the program will consider it as an invalid input. All the 3 cases you'll get invalid input, except maybe for the third case, where sometimes you'll get valid input. And this will again test if the program is handling invalid inputs correctly. It should not do anything. It should raise an exception and stop. So now all these rules that we saw, 4 rules, which is terminal replacement, non-terminal replacement, terminal and non-terminal duplication, terminal and non-terminal deletion, they can be applied for XML example that we saw again. For the sake of succinctness, I haven't really worked out an XML example. Feel free to ping me in the forum if you have any doubts, and I'll be able to explain it to you. When specifically for XML, people usually design mutation operators that check for constraints. Like in the earlier thing we saw, right, that ISBN must be a 10-digit numeric string. So they will make ISBN a 0 empty string and see how the program handles it, and so on. So they design to work around the constraining artifacts to create invalid inputs with reference to the constraints. So here is a summary of mutation testing. This will be the end of mutation testing that we will see. Mutation or syntax-based testing is a very powerful testing technique, as I told you. It subsumes several other coverage criteria, as we saw in one lecture module. They are based on the underlying grammar of the software artifact. For every programming language's grammar is available. For inputs, whenever grammar is not available, it's a worth exercise to derive the grammars for these inputs. Mutation, when applied to programs, result in mutated programs. They have to be killed by designing test cases. We saw two notions of killing, strong and weak killing. Whereas mutation, when applied to inputs, directly result in test cases. So there is no notion of ground strings or killing mutated programs. And specifically, if you're interested in doing mutation for Java, I recommend that you check out this tool that is available as a part of a project from George Mason and a university in China. It's a pretty good tool to do mutation for Java programs. I also know of a couple of other tools for mutation for XML and for old Fortran programs, which is a very good tool called Motra. But feel free to Google for mutation tools for other kinds of languages. So in the next lecture, I'll give you a summary of what we've done till now. Thank you.